in time. Okay, so now it's recorded. Okay. So the second talk is about traveling in time while debugging using RR by Adrien, Bustany. And RR is a tool for recording execution of a program, and you can replay it as many times as you like. We will see more about that soon, I think. And Adrien is a Gopher of the first hour and has been using it for work for around 6 years now. And he also likes mountains and gummibärchen and debugging tools, of course. So welcome, Adrien. Please start. Show your screen.
Yeah, thank you for the introduction. Okay, so I'll share my screen. I hope it's going to work correctly. Please tell me if not. Okay, sorry, up. Cool. Okay, so I hope, yeah, I can hide the video for now. Right, so hi everyone. Yeah, so I'm Adrien. I'm going to speak to you tonight about a really cool, I think, debugging tool called RR. And I'm going to try to show you how it can hopefully make your life easier when you're trying to debug complex issues. I'll start very quickly with a few words about myself. So I'm currently a backend engineer at Back. So as I mentioned in the announcement, yeah, we're like a small, like 14 people company trying to build a better product for servicing internal employee requests. So if your company is using like a super old, crappy product for that, you might want to talk to us. And yeah, we're hiring our first machine learning engineer now. So if you feel like you could build up a team and contribute to the product, then please get in touch. Apart from that, as Oli mentioned, yeah, I've been doing Go for quite a while. I've started even like before the 1.0 versions for fun, mostly back then. And my background is a mix of both like backend engineer, but also like system engineer, and also like I've done some embedded programming. I started at Nokia back when they were still doing phones. So we had like our fair share of weird grading issues and like tricky problems to debug, and I wish we had RR back then. So yeah, let's get back to the subjects. Wait, I realize I don't see the chat here. So if anybody is asking questions, I don't see it. I guess that's fine for now. Okay. And then the menu is not appearing anymore. Awesome. So yeah, let's start. Well, okay, whatever. So yeah, let's go back to the subject. Sorry about the Zoom mess. So yeah, like R is a debugging tool. So let's maybe take a step back and try to wonder, okay, like, what happens when you have a bug in your program? So usually the first step is like realize that something went wrong. I would say that's usually the easier part because, I mean, yes, you figured out something goes wrong, and that's like maybe something super obvious, like you have like a nil pointer at the reference, or you have like a value which should be like between 1 and 5, and like suddenly it's 20. So I mean, it's not always easy, but I would argue that usually like observing that something went wrong is the easier part of the issue. And then maybe you're lucky and you figure out, okay, it's just like a missing error check or a missing nil check, and the fix is also quite obvious. But then sometimes you stumble into those kind of bugs where the root cause is actually hiding a bit further. So it might be that the software had to go through like a number of internal states to reach the state that is now buggy. So there is always this question of like, okay, like how did we get to the state that is, now displaying this this abnormal behavior? So I mean, there are a couple of approaches to try to diagnose how we got there. There is one which is not really like scientific, but confess I'm using it quite a lot. It's just like, you put some like printf goals all over the place in the code. Not very elegant, but it works. Especially if you're using version control, you always know it's like super easy to discard the changes afterwards. So it's fine. You just have like your build with like many more log messages. If needed, you can even usually deploy it to your production environments, maybe on like a subset of hosts, and try to figure out what's going wrong. If you're working on more constrained systems like embedded systems, it's also usually an approach which works, because you can't run a debugger, for example, on a small embedded board. So, I mean, it's good, but it only gets you so far, because I mean, you can't put a printf after like every single line of code, and then if you have too many of them, of course, you end up with heaps of logs, which are then some hard to process. So, like if you find you're starting to write a script to process your log messages, then maybe it's time to take a step back and consider another approach. The other obvious approach to like trying to figure out where things go wrong is just like to start a debugger and to decide, okay, I'm going to run my program inside a debugger. So yeah, I mean, it has like a slightly higher cost, which is I guess mostly mitigated if you're using an IDE, which makes it much more convenient. But else, like if you're using like just like the CLI, like setting the breakpoints takes a bit of time. You don't really know where to set the breakpoints at the beginning, because I mean, okay, like you know what's going wrong, but you don't know why things are going wrong. So you still have to use kind of like wild guessing of okay, like where would be the relevant breakpoints to set. Usually, I would say that with most debuggers, the overhead is quite higher. If you're working on a desktop machine, it's usually not a concern. I mean, even if your software is running like 6 times slower or 10 times slower, it's most likely still okay. But it also means like you can't really deploy a build in your production environment that's running inside a debugger. So that's most likely not going to work. And I mean, yeah, it also gets like messy quite quickly if you end up like having 10 breakpoints all over like the course of your program. Then like you keep having to like step through all of them one by one, and then like if you realize like you went too far, then you have to restart from the beginning and like again like step through all the branches. So I mean, it's of course already much better, but like we can still do like I guess even better. There is a common point to both the approaches we just like discussed about the like the printf statements all over the place and using a traditional debugger like Delve or GDB, is that basically you are mixing the running of the program with the analyzing of the program to try to figure out what goes wrong. And that's where RR comes into picture, because the idea of RR is, okay, what if we could like run once the program and then like record what happens and then like replay the same build many times. And that's actually a fairly interesting concept, because there is like a whole class of issues that are really hard to reproduce. So when you speak about race conditions, for example, or if it's just like maybe like your service, like service is lots of requests, but only one kind of request that happens maybe like once a day triggers your crash, then it might be that just like reproducing the issue already is hard. And if you decide, okay, like you're just going to record like the whole execution of the program until you get to this failure behavior, then once you have this failure, you can replay it in a deterministic way over and over because you have this trace which is recorded. So that's the idea of RR, which is a tool which was originally developed by Mozilla for Firefox. So like they really needed a tool which is practical and which scales to larger programs. So I mean, I imagine like like Firefox is a pretty large code base, which is a mix of C++ and JavaScript, and I mean like Rust nowadays. So like many languages cooperating together, multiple processes. So they needed a fairly like robust tool that could handle like those large code base, that wouldn't have like a too high overhead. So RR is advertising, yeah, that your program should maybe take like a 20% hit when you're running in recording mode. And like RR is also a tool which is fairly easy to use in that you don't need any special kernel modules or any special hardware. The only thing you need is a Linux system. If you're working under Mac OS, then you can also run RR inside Docker. They have a page on the wiki of RR which explains how to configure Docker so that RR can run in there. But Docker needs to be configured with additional privileges so that RR can use the APIs it needs to interact with the kernel and to record the process correctly. So okay, like we've discussed about this idea, okay, let's record a program, let's replay it many times, but like how do we record a program? Because in the end, I mean, the program is running on the CPU, so you somehow need to virtualize the CPU or to be able to, slip the recording layer between the program and the CPU. So it doesn't sound that straightforward. So yeah, the first approach is to say, okay, sure, I'm going to emulate the CPU completely, and I'm going to just like record every single execution that the program is executing and dump that into a trace, and then I will replay that trace as many times as we want. So like the virtual CPU approach is something that, for example, Adrien does. It's maybe not so popular in the Go world. It's a tool which is used for diagnosing memory leaks or like race conditions. It's also a very good debugging tool. So the thing is, like, it comes with a pretty high overhead, which makes like debugging much slower. So there is also, yeah, sorry, I was just checking the chat. Yeah. There is also, yeah, so backward, sorry. Then one other approach is to realize that when you're running a program, you have two classes of code, basically. There is code which is deterministic. So for example, if you're doing an addition and you're adding 2 and 3, then like every time you add 2 and 3, you're always going to get 5 as a result, hopefully. So you have that code which you don't really need to record because you only need the inputs, basically. And all the rest just like follows because it's a pure computation that does not depend on, inputs or outputs or like the current time or some random number generator. So that's one class of the code. And then you have like another part of the code, which is the one interacting with the system that is going to do like those network calls, like reading files, reading the current time. So the idea of RR is like you're just going to record those interactions with the outside world, so to say. And that's going to be much more efficient. So it's going to produce a trace which is much more compact and then like so much easier to use afterwards. It also means like you can really run the binary as it is. The Linux kernel has facilities for intercepting those calls to the kernel so that you can record them. That's kind of like for the theory part. You don't really need to know anything about this to actually use RR. And we are going to show that. So in practice, you just run like RR once or many times, depends, to record the runs of your program. And then you use like RR replay or DLV, like delve replay on the trace. So if you use RR replay, it's going to use GDB as a front end, which is not always the best choice for debugging Go programs. If you're using delve, I mean, you're having a nicer Go experience, but delve is still missing some feature compared to GDB, namely watch points, which we will add afterwards in the demo. So there is like a couple of use case which I think RR is really good for. So we mentioned earlier that it's really good for diagnosing hard to reproduce issues because like you can just like record your program in a loop and then like stop your loop as soon as you hit this this bug. But it's also good at recording stuff when like maybe you don't have like a unit test covering this part of the code and you have, for example, like your UI is like hitting like 6 different endpoints on your backend before you exhibit the problematic behavior. So you might decide, okay, I'm just going to record my backend process using RR, and I'm going to click through my UI, and then I can replay that trace over and over without having to click again through the UI through those like 6 or 7 different steps to get to the bug. So, and you might also like it's even useful for replaying, like for example, like network interactions without hitting the network again. So in distributed systems, it's actually like a super valuable tool because all those network calls have been recorded in the trace. And so like every time you replace a trace, like they're not done anymore, but your program thinks that they are done anymore. So okay, let's get maybe a bit more concrete and take a small demo. So I have like a small program here, which I try to keep super simple. So it's a simple HTTP server that serves user profiles. So we can see that we have this function called load users that returns a static list of users. We could imagine that it loads them from like a file or a database or whatever. And then, so there is a bug that I guess most seasoned Go developers will see right away, but which is maybe a bit less obvious for Go beginners, which I'm not going to explain now, which we're going to find out using our R. So what we do is like we load the list of users, we store the users, like we index them in a map by their email address, and then we declare like an endpoint on our HTTP server, which allows us to retrieve a user profile by the email. And the last lines are just like basic starting of the HTTP server. So I mean, if we go back to the user list, so we see like we have Alice and Bob and Mallory, and each of them with their email address. So we should be able to just like start the program and ask for the name of Alice and get back Alice. So let's see, let's compile the program and run it. So here I have the server running on port 1412, and we are going to create this API and try it with Alice. Oops. So here we see that the result is not really what we're expecting. And now we want to figure out, what's going wrong. So I'm going to recompile the program, disabling all optimization so that we can have like slightly nicer display in the debugger. So the -N is disabling all optimizations, and the -L is disabling inlining, if I'm not mistaken. But else it's basically the same program. And I'm going to run like my server again. So I mean, like we can check that even with the optimizations disabled, it still exhibits the same behavior. I'm going to record an execution of this program. So I start the program just normally, but like inside our R. So RR displays where it's saving the trace. In this case, in my home directory. And I'm going to hit my endpoints using curl. Okay, so still the wrong answer. So here I can just like use Control-C to kill the program, and the trace has been saved. I'm going to show you how to expose the trace using both delve and GDB. So let's start with delve. So I'm just going to delve replay and then like give the path to the recorded trace. So this is a normal delve UI. So here, why do we know? So we know that basically the result that we're getting is incorrect. So if we go back to the code, so we can see that, yeah, it's line 42 where we print a name. So let's set a breakpoint at line 42, and then like just go all the way there. So here we have hit our breakpoints. So as you can see, like I didn't have to redo the curl stuff. The HTTP request is part of the recorded trace, so it just replays. And so here, if we check like the user.name, it's indeed Mallory, which is the incorrect answer. So we can also like try to see the user, and we see that okay, the user is really not the record that we expect. So we can also like I think it was the name of my dictionary. Yeah, like try to look what's in the dictionary, and here we clearly see that something is wrong because yes, we have our 3 entries, but all values are wrong. So now, okay, like most likely something is wrong in the code where we build this dictionary, this map. And so this is at line like 20, 29, 30. So we could either kind of like quit delve and then restart it on the same trace and then put a breakpoint at line 29. But I mean, it's a recorded trace. So we've been going forward with a continue, but we can also go backwards because we can place a trace both forwards and backwards. So let's maybe like try to put a line, put a breakpoint at line 29. So I'm going to put a breakpoint there. And then I don't do a normal continue, I do like a reverse continue. So now I've walked my program execution back all the way to when I was at line 29. So if I look at what's in my map now, I have an empty map because it's the beginning of my for loop. And now I can step again in forward direction. So I can see that my map is still empty. And my user is Alice. If I step again, now I have one entry in my map. And the user is still Alice. If I step again, now I'm again inside the for loop. And here I can already see that something has gone wrong. So this is a pretty common example and a pretty like tricky. I mean, it's a mistake which is easy to make in Go. Luckily, there are some linters which help you catch this kind of mistake. The issue is that in the for loop, the user variable is like as a stack is a stack variable, and it's not being reallocated for each iteration. Like the value is just being overwritten with each item which is in the user list. And here at line 30, what we're doing is like we're taking the address of this user variable. But this address does not vary from one iteration to the other because it's always the same variable. So basically, like at each iteration of the loop, we are overriding this variable. And so we are overriding what has been stored in the map. So we can see if we step again. So now we have like the two, like everybody is Bob in the map. And if we step again, now like everybody is Mallory. So in this case, we were lucky. It's a deterministic issue, so we didn't have to record like many times until we found we found the run with a bug in there. But I hope it already shows a bit like how useful it is to be able to step like backward and forward. So I could do the same and again like step backwards and see that the map empties again like progressively. So it's a pretty simple example here. And I knew that it was only so few places, right, where this data could be set. I knew that only at lines 29 and 30, I would be filling this map. So it was pretty obvious where the root cause of the issue could be. Now, if you like take like a much more complex program, so for example, Billy was talking about like, state machines. If you have a state machine which has been going through, I don't know how many transitions, it's not always that obvious, like, where things went wrong. And there is a pretty powerful tool for diagnosing those issues, which is called watch points, which basically means that you ask your debugger to watch a certain memory address and to break as soon as this value changes. This is usually efficient enough because it's backed by some CPU support. So like you don't have to stop at each instruction to see if the value has changed. Watch points are not supported in Delve right now. I think there is a ticket open for that, but GDB supports them. So I'm going to, like analyze the same trace again, but using RR replay, which is going to start GDB. So GDB is going to be a bit less nice in terms of UI, but we can see that we can like basically do the same thing. So let's break at line 42, where we display the name of our user. Let's continue all the way through there. Let's look at the code. So we're at line 42 here. And we can see that user name is indeed Mallory, which is not what we want. So what we can do now is ask the debugger, okay, like please tell me where was this user.name value set? So what we're going to ask is like, what is the address of this value? So like this 0xC00 and something is the address of the value. So small parenthesis, like one really interesting thing with the fact also that we have like a single recorded trace is that from now on, every time we replace a trace, every variable has the same address in memory. So it means like if you have like a really complex issue and you've been like saving some GDB commands in your file, then you can like perfectly quit GDB and relaunch it. And like you'll say, if you have been breaking or watching some memory addresses, those memory addresses will stay the same across each replay, which can also make life quite easier sometimes. So I'm going to ask GDB to watch this value. So here it tells me like it has like a hardware watch point, which means like it's backed by the CPU, so it should be rather efficient. your CPU only has a limited number of watch points, so you can set like 200 of them. I don't remember how many it is, but I've never run into cases where it was not enough. And so now I'm just going to reverse continue. So I'm going to rewind the execution of the program, and GDB is going to stop where this value was set, and which is exactly at the line of the for loop because of the issue we were discussing earlier. So it even gives me like the address of the old value and of the new value. It's not super trivial to print those things because like the Go support for GDB is still quite limited, but we know it's a string, so we can ask GDB to like print the first 3 characters of each value. So here we can see that the new value is Bob and the old value is Mallory, we suppose afterwards. The meaning of old value and new value is a bit confusing here, but it's because we were playing the execution backwards. So the new value is actually the old value, and the old value is actually the new value. And so here you can really see that we're at the line where things go wrong. And so it like in a single command, we're able to pinpoint like, you know, what was the origin of the issue. So basically like this combination of like being able to play a trace backwards and forwards combined with watch points and /or breakpoints or even conditional breakpoints. So like where you ask the debugger, okay, like break at this line only if the value of this variable is equal to this value, makes exploring program executions and trying to find bugs much easier. So that's pretty much all I had for this demo. The timer says I'm 25 minutes into the talk. I don't really have any much to say about RR. So I guess I'll cut the talk here, and I'm happy to take questions. So yeah, I'm gonna try again.
Thank you very much.
Maybe I'll stop sharing my screen. Sorry.
All right.
Because Zoom doesn't allow me to hide private messages, and it's a bit embarrassing. Maybe there is a clear button somewhere. Not even.
Settings have changed, so anybody can unmute themselves and ask questions. Good time to stop the recording.